เห็นยัง น้องอาจารย์เขาคุณทำอะไรไอ้ดีเดย์อะไรlet's can we wrap up the class tomorrow? So tomorrow we have a class at 2 o'clock. Can we? Usually we have class on Wednesday. Okay, and then we try to finish everything tomorrow. Okay, and then on Friday we don't have class. 2 o'clock, just like the way that we learn. 2 o'clock. Talk about tomorrow. Friday no class, so we learn tomorrow at 2. Okay, just like normal schedule. No class. Okay, the same place at 2 o'clock in that room. พี่แอนฝากไปบอกเขาด้วยนะเรียนพรุ่งนี้ 2 o'clock. Okay. And then tomorrow I let you know what will be in final exam. Okay, but what we will learn today, okay, it might be in final exam too. Depend what we up to. Okay, but we got one more question in the final exam that you haven't learned. Okay, it might be in today's lecture or maybe in tomorrow. Okay, let's look at the hash function. Okay, again, the idea of hash function, we want to build a function that we can locate the data. Okay, according to the data itself. Okay, we passing the data to the function. The function use that data to calculate location. And then we can store the data in that location or we can access that data in the specific location. Okay, there is one example how to create a perfect hash. Okay, what is a perfect hash function? It's a function that has every function has one output. In terms of mathematical function, every function has one output. No function has two output. You may have two different input, have the same output, but you cannot have one output produce two output. That's not a function, right? You learn in discrete math. Okay. So what is a perfect hash function? What we don't want in a hash function? Okay. When two input or two data, when you pass into the function, it returns the same location. So you cannot store two things in the same place. We can store one thing only. Okay, so for that case, we want the hash function to return different output. Okay, for different input. Okay, you don't want to have two input with the same result. In other words, we don't want two data to have the same location. Okay, so that's the perfect hash. For example, okay, there is a person named Chichili. Okay, he come up with the idea to perfect hash function. Okay, this is the way that he going to calculate it hash function. Okay, it hash function calculate from the length of the word that's gonna pass into the hash function, okay, plus, okay, the G function that will get the input from the first character of the word, okay, and another letter is the last letter of that word pass into the same G function. Okay, what is a G function? It's a function that we have to find out what it is function. Okay, again, the input of Cicilline method is a word. Okay, this word, okay, when you pass into the hash function, it's gonna be calculated according to this. Okay, number one, find the length of that word. Number two, take the first letter of that word, pass to G function. Okay, and number three, get the last letter of that word, pass to G function. Okay, and add these one together, and then mod by the size of the table that we want to store these words. Okay, which one that unknown for you? You want to calculate this H, calculate from here. Which one you don't know? Huh? Okay, let's say you have a word. Okay, can you find the length of the word? Yeah, you can. Can you know what is the first letter? No, you can. Can you know the last letter? Yeah, you can. Mod of the size of the table, we determine how big is this table. If you want to have 100 values to store, then you can have T size 100. Okay, so which one is unknown? G. G is the one that we don't know. And because what is G? We don't know what is G. This is what Cicilline want to find. What should be a G function so that we can make this hash function to be perfect. In other words, the hash function of a word that we know will have different results. Okay, so the question is, what would be the G function? Okay, so Cicilline try to find what is the G function that make the whole thing here become perfect hash function. In other words, it doesn't matter which word you pass it in, it's gonna be no repeat answer, no repeat output. Okay, but again, the Cicilline method is just the idea. Okay, make you try to think that how can we figure out the perfect hash. Okay, Cicilline method work on certain word. Okay, if the word list change, then the G may change. Okay. Okay. Let's look at example. I'm gonna jump. Okay, let's suppose these are the word. Okay, it is a word of they call milk. Okay, milk, they are like special Greek god, those people. Okay, they want to make perfect hash function for all these 9 words. Okay, how can we make the perfect hash function if we have these 9 words to store in our table, in our data list? Okay, we're gonna find out. Okay, what the G function would be. Okay, so the idea they use some kind of trial. Okay, and if it doesn't work, go back. Okay. The idea is this. Okay, again, make sure you remember the function. Use the length of the words plus, okay, the G function that we're going to find with the first letter and the G function with the last letter, and mod with T side. For example, okay, if the word is, let's say this one, euterpe. Okay, euterpe have the length 7. euterpe. Okay, so for this case, okay, if we pass to the function euterpe, this gonna be 7. Okay, and this gonna be G of E because euterpe start with E and also end with E. Okay, so the hash function, okay, for this case, it's the same picture. I just make it bigger. Okay, if it is just to play with the, okay, try and guess. Okay, so if G of E is 0, this is the if. Okay, what the hash function would be? Okay, so hash function of the Euterpe, okay, will be, okay, the length is 7, g of e is 0, g of another e is also 0. Okay, mod with the size. Okay, since we have 9 words that we want to make hash function for, okay, this is 9 words. Okay, so the table size will be 9. Okay, so the whole thing here, mod 9 is 7. Okay, so we just try if we give the g function with input e, okay, would be 0. The value of hash of this Euterpe will be 7. Okay, and then continue, pick the second word. Okay, let's say the second word is Calliope. Okay, with the Calliope, okay, we're going to need to find the g function for c. And since we already assume that, okay, if g function of e is 0, what is going to be? Okay, so here we're going to continue, define, let's suppose g of c is 0. If g, number 1, it is the first try, we try g of e 0. We try g of c also 0. Okay, if g of c is 0, hash of this, what the word again? Calliope. Okay, what's the hash function of this one? It is, length is 8. Okay, g of first letter is 0. We assume that, let's say it is 0. Okay, g of last letter, e. G of e we said 0. Okay, the whole thing mod with the size of the table would be 8. Okay, so the hash function for Calliope would be 8. Okay, so far, do we have any collision? No. 2 inputs have different location. So then there is no issue. We can continue. Okay, so for this case, we pick the third word, Irato. Okay, and then Irato, we already guessed GE is 0. Now what we need, what? GO, because we never know what GO. Okay, let's suppose G for O is also 0. Okay, so then that would be the length of Irato is 5, GE is 0, GO is 0. So 5, 0, 0 is 5. And the hash function of Irato will be 5. And also mean we had no collision. So far our 3 guessing are good. Okay, we try with this G of E, G of C, G of O, all of them become 0. We had no collision. And we keep doing this. Okay, pick a next input, Terpsichore. Okay, so let's guess again. Okay, GT is 0. Okay, GE is 0. And the length of this one is, what's the length of this one? 11. Okay, if you count the number of the letters, it's 11. So it's 11 plus GT 0 plus GE 0. So 11 plus 0, 0 divided by 9 is, mod 9 is 2. Okay, so the result of hash for this input, Terpsichore, is 2. And so far we have no collision. Understand? Okay? No? Again, what we want is to figure out what is G so that the hash function will be perfect. Okay? The hash function, again, we want to try perfect hash, is a function that had no collision. If we pick G for a letter that causing us a collision, we're going to change that G. Okay? So far, we guessing G. Again, G will apply for first letter and last letter. Okay? So G of, so far we have figured out G of C, G of E, G of O, G of T so far. Okay, with all those try, okay, GC, GT, GO, GT, try with this, with 0, we have no collision. Okay, this is a word that we already tried, 4 words. Okay, and when we saw, we continue the same thing. We try G of M. Let's say we try with 0 first. Huh? But by H2, okay, because the length of this one is 11. So 11 plus G of T, and we assume GT is 0. And G of E, because that word ends with E, okay, it's also 0. Mod 9 is 2. Okay? Okay, so here we guess G of M is 0. And this one is how many characters? 9. Okay, so it's 9 plus 0 plus 0. Because GM is 0, GE is 0. Okay, so it turned out to have hash become 0. And 0 had no collision. Understand? So far we try with all these G value. Sorry. Oops. Okay, G of these 5 characters, we have no issue. And we continue. Okay. Try G of T. We already have, no, don't try to try. We already defined GT 0. GA, we didn't ever have it. So we try GA 0. Okay, with the GA 0, length is 6. 6 plus 0 plus 0 is 6. Mod 9 is 6. And again, so far, no collision. Okay, for this one, we already have G of C, we already have G of O. There is nothing to guess over here. Okay, it's a 4 plus 0, 0 hash is 4. Okay, now we try another word, polyhymnia. Okay, let's say G of P is 0. Okay, it turned out to be 10 plus 0 plus 0, mod 9 is 1. And at this point, no collision. And now let's see, we try another one, urania. We guess U is 0. And it turned out that if we guess U to be 0, okay, this length is 6. 6 plus 0 will be 6. And now this one is collide with that word. Okay, if we guessing GU is 0, we're going to have a problem of GA 0. Because look like we're going to have these two input have the same output. And that make no perfect. Okay, so for this case, we must not use GU 0. So then we try GU with something else. Okay, let's say we try GU with 1, and then we calculate. Okay, 6 plus 1 plus 0 is 7. It would be 7. And this one hat is 7. Collide with that one. Okay, with the U equal 1 also doesn't work. And then we keep trying. Okay, and let's say for this example, they will try for 0 to 4. Okay, if it's 0 to 4, look at it. If we try U0, U1, U2, U3, U4, all of them collide with with the one that we guessed before. Okay, and let's say we set the triad between 0 to 5. Okay, and then if we try up until 0 to 4, sorry, try up until 4, none of them could make this head function work. Then what we do? Then we go back. Maybe P is 0, doesn't work. So then we change P to be 1. Okay, so instead of GP 0, we try GP 1. Huh? If we try GP 1, okay, then we try to put into the head function what it is the length of, what's the length? Length is 10, right? 10 plus 1, 11 plus 0 is 10. Sorry, 10 plus 1, 11, sorry. 10 plus 1 plus 0 is 11. So 11 mod 9 is 2. And it turned out 2 will collide with that one. So then won't work. Okay, so P cannot be 1. GP cannot be 1. So this also doesn't work. So then we change again. Try GP equal 2. Okay, and when we try GP equal 2, okay, 10 plus 2 plus 0 is 12. Okay, and then 12 mod 9 is 3, and look like 3 does not collide with any of this. Then so far this look good. Okay, and then we try urania, in other words. We try U with 0, crash, collide with that 1. Okay, try U with 1, collide with this 7. Try U with 2, collide with this 8. Dot, until we found, try U with 4. Okay, when GU is 4, the head function return 1 again is the 6 plus 4 plus 0, because we define GA is 0. 6 plus 4 plus 0 is 10. 10 mod 9 is 1. And look like 1 does not collide with 3, does not collide with this 4, 6, 0, 2, 5, 8, 7. Okay? And it is all 9 words. 9 words that we plan to put in this hash. And look like all 9 words with this G function. Okay, GE0, GZ0, GO0, GT0, GM0, GA0, GP2, and GU4 with this G function. Okay, according to the 9 input, we will have perfect hash, no collision. Okay, and that's the G function that we're looking for. Okay, if we have G function like this, with the way that Chili want to calculate hash function, it look like this hash gonna be perfect. If our G look like this, for these 9 values, 9 mules. If it not need 9 mules, it would be different. Understand? Okay, again, this G work only for this input. Okay, for these 9 words only. If you have other words, then you may have to change the G. Okay, and if you have more than 9, then the T size also have to change, not 9. Understand? That's an example. Okay, how to create a perfect hash function. Okay, again, the hash function here is composed of, okay, the length, okay, and the G function that define from first letter and last letter. It is up to you. You want to try to make perfect hash, you can use many letters. It's up to you. Okay, and then you can use this one, not plus. You can use whatever operation that you want, as long as you use something we call backtracking. Okay, to try until we found the G that make the whole thing perfect hash. Okay, again, what is backtracking? Remember the mouse that run on the maze? If you go forward and it doesn't work, then you move backward. Okay, if you move backward 1 step, still doesn't work, then you move backward 2 steps. Okay. So for this case, we move forward. Try E, try C, try T, try M, try A, try P. It works so far, but when you get to U, none of these work. So then we move backward, shoot to P, change P to 1. Okay, it doesn't work, change P to 2. Try again until we move forward and we found the final answer. For this case, all words can have the perfect hash. Then we stop. Okay, it is backtracking, okay, to make the perfect hash. Understand? Okay, just an idea. There is a way to find perfect hash. But again, this perfect hash have many limitations. Okay, for example, this perfect hash only for these 9 values, 9 mules. If it's something else, this one doesn't work. You have to recalculate. Okay, and this perfect hash actually take a little bit more time to find out what the hash function. For this case, the hash function depends on G function. So we have to define G function. Understand? Okay, so there is somehow to create perfect hash. But in the real world, if you use just any word, make a perfect hash is a little bit hard, but you still can. Okay, for example, can you make perfect hash on any word in dictionary? I think you can, yeah, but you gotta run something like this for a while to test all the words in dictionary. Your G function might be a little bit complicated. Okay, gonna be something long. Okay, you have to use backtracking a lot. Sometimes you work backtracking might not work. Okay, so you may have to go back a lot. Okay, it depends on how many you try. Okay, if one try only 4, 0 to 4. You may try more, 0 to 10, 0 to 1,000. Okay. Okay. And again, to make a hash easier to be defined, okay, also dealing with the t size. Remember, if your t size is big, it's less chance to be collide. Agree? So this one, the t size, we use 9. Because we know we're going to have only 9 values. Okay, so if you t size 9, the mod is between 0 to 8. The chance will be collide is easily among these 9 words. Because you make perfect table size is perfectly fit to 9 values. But you make table size to be 100, the one would be less chance to collide. Okay, because you mod by 100, this might not be 2. This will be 11, it will be something else. Okay. There is another one in the book. Okay, FSCD, similar. Okay, but I will not go over. But the idea is similar. They try to define what the perfect has using different idea of hash function, but you still need to find G function. Okay, from the same list. Okay. Understand what is a hash? Okay. There is something else, nothing to do with a hash. I think I asked students last year, this for final exam question. Okay. You want to try? Go home, practice for fun. Can you do this? There is nothing to do with hash. Can you write Java to do this? You can. How many nodes is in the tree? How many nodes on the tree? Can you write program to do this? Write algorithm? How many nodes on the tree? Okay, what's the height of the tree? How many nodes? Okay, look at next one. How many leaves? How many right side? What the height? Can you calculate them? Okay, what is the height of the tree actually? There is nothing to do with the hash. There is review question from last year. What is the height of the tree? Huh? Always go left and how do you know this is not a heap? This is not a balanced tree. You may have a lot of nodes on the right, nothing much on the left. What is the height of the tree? The answer is amazingly easy. What is the height of the tree? Using recursion, you find answer amazingly easily. Huh? Dot, 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 dot. Let's see, no dot, dot, dot. What the height of these three? 5? How do you know it's 5? Okay. You go to the longer one. Agree? Okay. If you don't see it, what the height of this one? From here to here? 4. And then you plus 1 more. Agree? Okay? What the height of the tree from this root? Is 1 plus the height of the left subtree or the height of the right subtree. Huh? Yes or no? The height of this tree is 1 plus either this or this. No, it's still question. No. The answer is combination, not the first one. No, look at this tree. Let's say the tree is dot, dot, dot. It is a tree. A lot of things. A lot of things. What the height of this tree? If the height of this one is, let's say, for example, 10, this one is 20. What the height of this tree? 21. No, the whole tree is 21. Agree? If the height of this one is 15, what the height of the whole tree? 16. If the height of this one is 8, what the height of the whole tree? 11. So what the height of the tree? Is according to that. Kind of if, okay. Before if, what you do? Either right or left, and then plus 1. Good. It's the 1 plus the recursive call height of left of this T node. Okay, let's say T dot left. You pass T dot left. Actually, this is not a tree. You can say I pass the node. That would be a root, node N. You pass the root first, and then after this one going to split the height of the left subtree and the height of the right subtree. And then what you do between the two? Max. Which one is higher? We add 1. Either left or right, which side is higher? We use that 1 plus 1. That's the height of the whole tree. Is it complete? No. What we miss? Recursion. What we need? Anchor. Good one. What's the anchor of this one? If, and that I call n, okay, n sub left and n sub right. If n equal, now, good. What we return? 0. Done. That's the height of tree. Yeah. If one node have only left child, no right child, what would happen? That one gonna recursive call the height of this node and recursive call of this one, but this one is now return 0. But this one have, we don't know yet, but this one, if this one have no child left and right, so then the height of left is 0, height of right is 0. It's a 1, 5, max of 0, 0 is 0, and it is 1. Use recursive function, recursive method. You can find it easily. Understand? Again, what the height of this subtree? What the height of this subtree? It's going to be 1, right? That 1. 1 plus the height of this one. You're passing now. But when you pass the now, it's 0. Okay, so it's a max between it is 0. And this one node. One node gonna call the height of this 1 plus the max between height of this is now. Height of this is also now. So max between 0 and 0. And that is the 0. So 1 plus 0 is 1. And max of 0, 1 is 1. And 1 plus 1 is 2. And here this one, the height is 2. Same thing with something higher. Understand? So now, can you count how many nodes on this tree? Hey, the whole tree have so many nodes. Good. How many nodes on this tree? What you return? You start from the root. Is 1 plus the number of nodes of from the left, and the number of nodes plus the number of nodes on the right. Instead of max, you use plus. Recursion. Same thing. Okay. That used to be exam last year. Number of leaf. Number of nodes, sorry. Number of nodes. How about number of leaf? Number of leaf. How many nodes which are the leaf? If we start from root, if this one have 2 of them, should be plus 1? Or at least have only 1? If they have only 1, at least 1 child, do we count that one as a leaf? No. We count as a leaf is no children. So how many leaves? How many leaves on a tree? So start from root. If that node have either left or right, then we don't plus 1. Agree? The number of leaves. This one doesn't count. Okay? If they have left or right, we don't count this one. If we go down until at the bottom, this one have no left, no right, then we add 1. So we may add 1 or may not add 1, depend on that node itself have children or not. If this node have at least 1 child or 2 children, we don't add 1, but we still recursive call both of them, yes or no? Because it is a node that have 2 children or 1 child. You still need to make recursive call. But you have to check whether the node have no children or not. If no children, return 1. No child. So what is the number of leaves? Agree? that number, please? If P is now no node, it's not a node for sure. Okay, but if the node, okay, have no left, no right, but that node is not a null. Okay, that node is not a null, but that node have no left, no right, then we return 1. Okay, but if there is a left or a right, then we're supposed to return recursive call, but passing left, and plus recursive call passing right. Okay, if this one is a root, have both left child, right child, we have to find out from there how many leaf. But itself had no leaf for sure, because they have left or right, or left and right. Okay, so if there is no children, then we count 1, return 1. Okay, if there is a children or more, we don't return 1, but we recursive call that node. Okay. Just for fun. Do at home, right? Child node. Okay, nothing to do with the hash. Okay, it's just a review. Okay, the last topic that we're gonna learn in this class is data compression. Data compression. Have you heard this word? What does it mean, compress? You use it many times. Yeah, what does it mean? Zip. Yes or no? And you zip a file, you make it small. Is it the same content? After you zip, what inside look the same? No. You have to unzip. After you unzip, it will look the same. Okay, when you zip it, the content doesn't look the same. But the key is must be smaller. Content is not the same, but after you unzip, it must be the same. Not zip, make it small, but cannot unzip. Then it's not really compression. Compression, you have to be able to compress and be able to uncompress, make it look the same. Okay, but during the time that you compress, it might not look the same. We don't care, as long as it's smaller. Okay. It is kind of data structure technique. Okay, how to make the data look smaller. Okay, content might not be the same during that time. Okay. There are many techniques to do the zip. Okay, we will look at one of them. It's called Huffman code. Okay, it's a technique that we try to make the way that you have words, organize them using different techniques to make the total size become smaller. Okay. Okay. Basic technique they call run length encoding. Okay. What is run length encoding? Okay, run length encoding, they try to make way that the data that repeat, we try not to make a presentation for it. It's called run length, depend on how long it's running, the same thing. Okay. For example, let's see for example, let's say you have letter digit 1111544. Okay, if we use 1 byte, okay, just an example. Actually, let's say 1 byte. If you use 1 byte, represent one number. That example. Okay, so how many bytes do we need? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Agree? This one will need 15 bytes to store. Okay? Can we use less than 15 bytes to maintain this value? That represent 1, 1, 1, 1, 1, 1, 1, 12 times, and then 5, 4, 4. The run length technique, they represent this one with this one. What is that? Is it? No. This is the same with this one. Look at it carefully. Run length. Anyone see? It is called run length. Look at the length. Okay. And he found it. How many one? 12 of 1 and 1 of 5 and 2 of 4. That is run length technique. Okay, so in total, how many digits? How many bytes? 1, 2, 3, 4, 5, 6, 7 instead of 15. You represent this one with this presentation. Okay, that is less space. Okay, how about this one? Can you use run length? Can you use run length? What is the run length encoding for this one? Example 1. What the answer? 3A 4 plus 2 slash 2P 6 greater than. Is it really safe? How many more bytes? Which one have more bytes? Which one or that one? Which one is less space? This one or that one? This one for sure. That one use like 6 bytes. This one for 6 bytes, I use only 2 bytes. Okay, this one 3 bytes. Okay, I use only 2 of them. Okay, so that one 4 characters, I use only 2 characters to represent it. This one means, again, forget about that picture. 3 consecutive A followed by 4 consecutive plus, followed by 2 consecutive slash, and followed by 2 consecutive PP, and followed by 6 greater than 6 times. Understand? Yes or no? Yeah? Here, you look at this one, you can unzip. Did it from here to here just like zip. Agree? You compress this one into this one. And you can decompress this one back to that one. Okay? The question is, you compress this one to this one. Can you decompress this one back to original? What did this one mean? If you don't see this one, you see only this. What does this one mean? It could mean 12, 1, 1, 5, 2 of 4. Or it could mean 1 of 2, 1 of 1, 52 of 4. And it's not this one. When you decompress back, you don't get the same answer. And that's totally wrong way to do. We don't do that way. Unlike this one, you compress into that. When you uncompress, go back to original. But this one, you uncompress, they don't go back to original. Sometimes depend on how you interpret it. Why? Why this one doesn't work? Why this one works? Why? We use a number to represent the length. And the data itself also number. This one, data has no number. So you have no issue with the length. Because the length is a number. Okay, so for this case, lan length might not work. Okay, for this case, number. Okay, can you use something else? Make your own way of run length to make this one work. How to make this one work? To make sure we understand it, 12, 1, 1, 5, and 2 of 4. Huh? Maybe we put comma. Maybe comma here. Then we would know that it means what. Oh, but still, if you put comma here, it means 12 of 1 or 1 of 21. Agree? Maybe you can separate something with colon, comma, colon, comma, colon, comma. One represents the value and one represents the length. Okay? Again, you may say 12 colon of 1, comma, 1 of 5, and then 2 of 4 like this. If you do like this, you can interpret back to original. Okay, but again it is numbers. If your data become character like this guy, then it is issue. We may have to do like in Java. What do you use in Java? Remember this one? The new line character. Okay, sometimes if you want to use this symbol, we use this one. Remember in Java, to represent backslash, you use double backslash, represent slash. For this case, if you want to really mean colon or you want to really mean character colon. Okay, so you may do colon, colon. To represent, did it mean to separate? Did it really mean colon? So to avoid confusing with this own symbol. Just like in technique of programming. But again, okay, if you try to make a lot of things, then it might turn out it not really reduce the size. It may turn out the length of this one may be the same with this length. So it's not really compressed. Okay? So run length not really work in many cases. Okay, work in some cases. Okay, but it is very famous in the zip file. Why? Why it works for this one in zip file? Huh? You know why it works in the zip file? Because sometimes the document that people write, they have a lot of empty space. Okay, empty space really have a lot. You mean run length here one way doesn't work if you try to put special character. But in some file, you have a lot of space, they look the same. Run length, even though you try to add special character, but if the repeating it very long, then would be okay. Okay, even though a little bit overhead. Okay. Okay, we can use ASCII code to encode character. Okay. Can ASCII code encode character? You know for sure, ASCII code. Okay, and encode any character. Okay. Okay, again, run length of this one will be what? 4A, 4B. What is the run length of this one? 1A, 1B, 1A, 1B, 1A, 1B, 1A, 1B. What the total? Total even longer than original. Keep adding a lot of 1 in there. Okay, so it's not really compressed. Okay, like I told you before. Okay. Let's see, for example, okay, if we try to make a symbol to represent character, okay, for example, if we use A represent by 1, B represent by 2, C represent by 12, okay, if you want to write, let's say the word cap, what is cap? Okay, let's say we want to compress the word cap. If we use code 1, let's see, coding 1, what the word cap will be? CAB, code 1, 1, 2, 1, 2. Agree? But if you use code 2, what is the cap? 1, C first. CAB, right? Okay, C is 1, 2, A is 1, 2, 2. Okay. Okay, how about code 3? C, A, 1, 1, B. Agree? It is CAB in code 1. It is CAB in code 2. CAB in code 3. Okay? Okay, in terms of compression, which one seems to be the best compression? Code 1, why? Because compression we want is small. Look like code 1 is the smallest one compared with code 2, code 3. Agree? Okay, look like compression in terms of size is good. Now, let's see, if you don't see the word cap, okay, you see 1, 2, 1, 2. What does it mean? Can you uncompress back to original? What did 1, 2, 1, 2 could mean? Huh? Could mean, what is this one? 1 mean A, 2 mean B, 1 mean A, 2 mean B. You write 1, 2, 1, 2, when you go back, try to decode back to original, it could be this. Or it could be what? Could be A, A, B, C. Good. Not CAB. Okay. Or could be what? C, okay. Or could mean C, A, B. We found it, cap. Okay, so you cannot decode or uncompress back to original. And it is not a good way to generate the code for this symbol. Okay, you can compress or you can encode only, but when you decode, it could mean different things, and that is wrong. You're supposed to decode back to original. Okay, so even though the code 1 looks short, but doesn't work. Okay, how about code 2? Code 2 work? 1, 2, 1, 2, 2. 1, 2, 1, 2, 2. Is it work? C, good. C, good. Oh, dead. So then we should not go CC. Okay, what should we do? 1, 2, 1, 2, 2. 1 mean A. 2 doesn't mean anything. 2, 1. Code 2, code 2. 2, 1 had no meaning. 2 alone have no meaning. 2, 1 no meaning either. 2, 1, 2 had meaning? No. So look like A start with 1 doesn't work either. You cannot continue to decode. So what should we do? Maybe start with C, but don't conclude it one as C. Is 1 for A and then 2 for B. Okay. So this is different problem than this. This problem, when you encode, you get the compressed value, but when you try to decode back, you may have different, you get the wrong value. This one, you can get the right value, but you have to try many times. Okay, you try with the wrong way, you end up with no answer. And then you have to try different way. Like I said, this one, try first time doesn't work, try second time doesn't work, you have to try again. Okay, so this one, even though it have only one answer, okay, but still you have to try many times. It's not really good encoding technique. But it works, okay, but it's not good. You have to try for many times. Okay. How about this one? Okay. 2 1 1 1 1 2 2 1 1 1 1 2. Huh? 2 only? Nothing. 2 1? See. 1 only? Nothing. 1 1? A. 1 only? Nothing. 1 2? B. This one you don't need to try error and try success. This one you try one shot, work. Okay? So actually this one doesn't look shorter than these two, but it's the only one that make decoding work. And this kind of coding is called prefix free. What is prefix free? The code that you use is not a prefix of any other code. Look at this one. This is not prefix free because this is a 1 and 1 is used for this one. This is not prefix free because some of these have been used somewhere else could mean something. This is not prefix free. The same thing with this. You have 1 here. 1 already been used. You cannot use 1 with something else. If you use 1 with something else, it's not prefix free. Understand? Okay, unlike this one, we have 1 1. Is there any start with 1 1? No. Did it 1 2? Is there any of these start with 1 2? No. 2 1. Is there any of these start with 2 1? No. And that is prefix free. If it's prefix free, it guarantees that you can decode back with original data correctly with 1 try, not many tries like this. Okay, because when it's prefix free, you try 2, it's not going to match anything. Then you're going to get 2 1, match with one thing. You try 1 alone, it's not going to match with anything, but 1 1 match something. Understand? Okay. So the way that we're going to do for compression, we should try to make code word in prefix free. How long you going to need? 60 minutes? Okay? Not really 60 minutes. A couple more slides and then we go home. We continue tomorrow. Okay? What do you think? Okay? Okay, let's look back at this one. Okay. We have A, B, C. Okay? Rule number 1. To make encode and decode work, we have to have something we call prefix free. Okay? Okay, we want a prefix free for sure. Number 2, what we want? If it's possible, we want them to be compressed. We want them to be short. Agree? Should I have, for example, okay, let's say I have code 4. Let's see, for example, my code 4 is A for 111, B for 121, okay, C for 1. Can I use C for 11? Yes or no? No, this is not prefix free. 11 is a prefix of somebody else. Can I use 12? No, because it's a prefix of that. Maybe 21. Okay? Because 21 is not prefix of any of this. 111 is not prefix of any of this. 121 is not prefix of any of this. This is prefix free. Agree? Okay, so here, both code 4 and code 3, they are prefix free. Which one you prefer to be your technique of compression? 3, why? Because 3 likely to use less digit, less byte than 4. 4 use 3, A, B use 3. Okay? Okay. Let's suppose we don't have this one. Just an example. Okay? Let's suppose we don't have code 3. Okay? Let's suppose I give you 2 choices. Code 4 and code 5. Okay? My A is 21. My B 212. My C 111. Between code 4 and code 5, which one you prefer? Code 4 and code 5, both of them prefix free. Okay? Between code 4 and code 5, which one you prefer? You don't need computer science to do this. You need the liberal art to answer this. Why 5? Huh? Starting with 2 and good. What does it mean? Oh, okay. You almost get to the point. Okay. She chose 5 because she said A use only 2 digits. And what is the good thing about that? No. Anyone love English? Kind of. Okay, almost right. Not just a vowel, but because A compared with B and C, A seems to occur in dictionary a lot. The one that most used in the dictionary should be small coding. The one that doesn't show much, it's going to have long length, yeah, we don't care. Like what letter? Z, okay, Q, that one doesn't occur a lot. You're going to have long length, we don't care. But if A has a long length or E has a long length, that's the issue. Because they occur a lot in our dictionary. Okay, so it's likely going to have a big overall. Okay, so here, good. Between code 4 and code 5, okay, look like code 5 is a better job to do compression. Because English words have a lot of A. You're going to use a lot of time that have only 2 digits. Okay, B, C doesn't occur that much compared with A. A occur a lot. Okay, so another word, okay, which encoding that we're going to use, it depends on the probability of occurrence of that character. If that one have high probability of usage, we should use the encoding that small. The one that high probability of usage. Like A have high probability that see in the dictionary. And the same thing with E. Okay, but unlike K, J, Q, that one have low probability of usage. That one, it could be long. Okay? Understand? Alright, we will look this one more in detail. It's called Huffman code. Mr. Huffman come with this kind of idea, okay, to make the encoding that small according to the probability. Okay? Okay, we look at this one tomorrow. And that would be the last thing that we learn in this class. Okay, we probably finish it tomorrow and then you can study after that. Okay, so no class on Friday, no lab on Thursday. Make sure you study. But I still see you tomorrow. Okay, and I let you know what will be in the exam tomorrow. Okay, have a good night, everyone.